Alright everyone, tonight we're going to be taking a look at this A2338, which is a 2020 M1 MacBook Pro with an interesting complaint. So this is a liquid damage MacBook that actually turns on and works. But if we adjust our backlight brightness here, let's sign in. Okay, we're signed into the OS and we see that the backlight works, right? So we're going to up our brightness. Everything seems to be working. I'm holding this at an angle because I don't want to show anything on the customer screen. And then we'll get to a point about right here and it shuts off, and we still see the machine is on because we still have our backlight slider here and the touch bar that works, but the backlight went out. And if I were to get a flashlight on here, so I'm just going to use my phone here, we could see that it still has image, but there is no backlight. That's going to be really hard to pick up on stream. So let's go ahead and open this up and see what's going on. There's going to be something up in the backlight circuit, and we'll go from what we find here, but it's probably going to be corroded capacitors, corroded traces, maybe corroded backlight drivers. Something is going to be messed up. So let's go ahead and jump right in, get the bottom off, and get this board out. All right, we have our bottom case off of this, and it's not hard to tell what's going on here. So if we look at this, we can see that there's some pretty heavy corrosion on the board, right around where our backlight circuit is, of course. So let's go ahead and take the board out and see what's going on. Pull the board out, give it a full inspection, and then go from there. But I'm pretty sure I know what's going on with this. The backlight circuit's fairly corroded and we could easily see that, so let's jump right in. Alright, logic board is out. Let's go ahead and get it under the microscope and see what's going on. First things first, let's just do a scan over the other side. Now, this around these components, but a lot of people misinterpret this as liquid. This is not liquid. This is flux staining from manufacturing. So if you see that, that is not liquid. And here's our CD3217s. This area looks pristine. This right here is a little bit of liquid that got on the edge. Not a concern. Didn't corrode anything. Just carry on. Here's our screen connector. It's unremarkable. These look like maybe speaker amps. Yeah, these are our speaker amps for one side. Here's a chip that appears like it doesn't have markings on it, and this has come up in the repair community recently, but turn it, it actually does. What it is, I don't know. I'm not going to look it up. There's no schematic or board view available yet for this particular board. We have some minor corrosion on one of our current sensing resistors right here. So we could probably use a previous schematic and find out what that is, but that's probably going to be a 0 ohm. We could probably just touch that up too. It doesn't look like it's that badly corroded, but definitely some corrosion there that needs to be addressed because that will not last. Here's our Renesas 501 CRB. This supplies PP3V3 underscore AO, PP3V8 underscore AON, which then drives our CPU buck converter. Now, here's where our issue is. This right here is our backlight circuit. This is all corroded. Now, all of this, yeah, it looks nasty, but it's probably not the cause of our problem. The cause of our problem is this little resistor here that you probably can't see. So this is going to be the VIN resistor of this chip. How I know this is, one, from previous cases, and two, this is the input side. This is the 5-volt input side to this chip, and this is what supplies this chip's power. Now, if the resistor that's supplying this chip's power looks like this, do you think it's going to pass power effectively? Absolutely not. So this little guy being corroded is probably going to be our issue, and we could actually see that little white spot in there is this, where that resistor kind of blew out internally. This is supposed to be a 0 ohm resistor. It's basically acting as a fuse. Apple, yes, if you want to use a fuse, not a resistor, but I'm not an engineer, so I can't speak. Anyway, let's see if this resistor is actually measuring 0 ohms. And how do I know it's a 0 ohm resistor? Well, technically I don't, but it was a 0 ohm resistor on the previous model's backlight circuit, which uses the exact same driver. And this is 386 ohms. 386 ohms is not 0 ohms, so chances are what is going on is that chip can work. The resistor is going to let voltage through. The resistor is just going to restrict current. But the backlight circuit will work at a lower brightness setting because it's using less power. The chip starts to use more power to create that higher brightness setting, and it can't based on the voltage drop is too high going through this resistor. So this is most likely going to be our problem here. Now, this area is corroded, yes, but this is superficial corrosion here, and I can resolve this by cleaning. This is a ROM chip for something, I believe. I don't know for sure, but either way, I'm going to show you that this corrosion is really superficial right here. Apple actually, this has actually been to Apple, and they sent it to their depot first, and they apparently said it's not fixable, but we're going to prove them wrong tonight. Yeah, so see, this corrosion is nasty, but it is superficial. There's certain capacitors that can stay and certain ones that can go. This is our keyboard backlight inductor, 'cause it's the same as the 2251. That capacitor, see that little black spot at the end of it? I do not like that. That probably has capsule infiltration, and that would risk shorting over time. I don't know what value that is, so what I'm going to do is just flick this thing off or remove it with my hot air, or we could just flick it off here. We do not need that there. It is not a big deal, and it is more risk to leave this guy on than to just flick it off, because one little capacitor like that is not needed, and we're not going to worry about it. Continuing on, a little minor corrosion here, a little bit by our touch bar controller. Speaker amp is corroded, not too badly though. That'll clean up nicely with some flux and heat. These are our keyboard controllers. These are corroded superficially. It's not that big of a deal. We'll take care of it. A little flux and ultrasonic. Let's go ahead and look at our 3v3 AON MOSFETs, which are under here. Our 3v3 AON MOSFETs supply our PMICs, which power the CPU, and look at that. We have corrosion under here, but it's not that bad. It only got a capacitor and a current sense resistor, so we should be okay. Again, same kind of deal on this capacitor here. I'm probably just going to flick it off because I don't know what value it is. I'd rather just leave it off than risk leaving something on. I'd rather just leave it off than put the wrong value and have the wrong value fail, because a capacitor is not really something critical in a circuit, at least in the application that these are being used as. So I do not think that one is important there. That's just for smoothing. We'll look closely, but that's probably just a PP bus or 3v3 AON cap smoothing, which is not that important. Otherwise, it's pretty unremarkable. Our CPU is under here. We will get into that later. But nice thing about this CPU is it's underfilled, so we don't need to worry about corrosion. What about under this shield here? So this is probably another PMIC. This is probably for our SSD, I'm guessing. This uses Hynix SSDs. Yep, as I thought, it's a PMIC. But it looks beautifully clean, so we're not going to worry about that. All right. Now let's get into our actual issue. So we have a lot of corrosion here, and we need to fix that. So how we're going to fix that is flux. So flux is that magical fluid that we put on a board, and it makes everything better. So let's do that now. And there's thermal paste all over my flux syringe. I do not know how that happened, but we're going to clean that off because thermal paste and flux does not mix very well on a board. And I'm just going to put a healthy amount of flux everywhere around here. Everywhere where I see corrosion, I'm putting flux down. This area is concerning here because, again, we do not have a schematic. We have nothing to know what's what on this board. On the 820-2016 we do, but not on this particular board. This is an 820-2020, and that schematic is not out there yet. There's actually a schematic for an 820-2100, which is the unreleased 14 or 16-inch MacBook, which is interesting, but I'm not going to talk about that too much. This is clean under here. But alright, let's get started now. So I am going to get on my hot air. I'm going to heat at 430. Put my nozzle on, the right nozzle on that I like. And we are just going to get that flux all melty over those areas, and that flux is going to eat away and dissolve that corrosion. That's what we want. We're also going to replace the corroded components that need to be replaced. So flux. And notice how that corrosion is just going to kind of disappear. Now this chip I'm concerned about. Doesn't look that bad though. Here's our resistor. Yeah, you could definitely tell that resistor is blown now by its appearance. It's burned. It has that coloration. That got very hot. Now my concern here is, did this blow from corrosion or did this blow from a bad chip? So I am probably going to replace this chip just as a safe side, because resistors can fail from chips failing like that. So this is a, let's see if we can see the number on it. Is this the same one as the Retina? I'm pretty sure this is the same that they've used since like 2012. 48B1 it is. Cool. So we're going to replace this chip in addition to that resistor there. The chip, we're just replacing it as a cautionary thing. It's probably fine, but I don't like my work to come back, so best just to get rid of it. Quick wave of heat over these guys. I don't want to melt that keyboard connector, so I just did a little bit of heat. That's all we should need. Same this one. These speaker amps I have to fully heat because they probably have junk under them. There. Good. That will come off in ultrasonic. I'm not really worried about the stuff that's not around the... I'm not really worried about like little isolated pieces of corrosion. Those aren't really a problem. What's a problem is when we have corrosion over components, obviously. Like this guy right here. These, one of those is a resistor, one is a capacitor. Generally, when they look like that, I like to replace them. Some stuff is going to be critical, but again, without a schematic, I can't just go guessing at values unless I know. The resistor, I can because I know what values that resistor is supposed to be, or I know in the previous application they used a 0 ohm resistor. So we can get away with that. Now, stuff like this, if I don't know the value of it, I can't just guess because we can cause problems. If I replace the capacitor with one that's underrated, it may work and then die. So we have either choice of knocking it off or leaving it on. Now certain capacitors, not all capacitors, can be just left off. So my rule here is if I can clean these guys up so they're nice and shiny, then they should be okay. If you could actually, sometimes you could actually see when the ceramic capsule in these are infiltrated, then that's not okay. A good example is that was the one that I showed you earlier. Now we have a bridge here, so we're going to take care of this. Actually kind of glad I bridged it because that allows all that junk to be sucked off and resoldered. We'll use our hot air on that one. So, hot air. Beautiful. Now these guys right here, I would like to replace that resistor, but let's see if we can touch it up. Sometimes they have a way of looking really bad when they're not, and the test is, just like I did on those capacitors, if I can make it look shiny and nice, then it probably is okay. And obviously this board is going to get a nice ultrasonic bath when it's done. Yeah, see that? I made these look nice and shiny. They're fine. That's all that's needed there. So, speaker amp, that capacitor is also, again, what I'm looking for, I'm looking at the inside of here. So what I'm looking for to see is if this cap is all ruined at the end, and falling apart, that means that liquid could have got in the capacitor itself. But if the cap is actually intact, the chances of liquid getting in there are pretty low. So that's what I'm looking for. And the caps are fine on these. The actual end cap of the capacitor itself is fine. So I'm going to do the same thing that I did. I'm just going to touch my iron to it with a little bit of solder and flux, and it should just get all of that junk that was on there out. That gray, that's all oxidation, and we're going to use an excess amount of solder right here to kind of get rid of it all. We don't want to overdo it on heat either. So if you see your solder kind of acting like that, more flux. Just like that. See that? Turned out really nice. I think we still have a bridge there. I can't tell. Nope, looks good. Same thing with this guy here. Looks good. Now I'm just going to give that chip another reflow to wash any junk out and fully set those capacitors in. Now again, I can't say this enough, this is not the same reflowing as like reflowing a CPU or something like that. This is totally different. There we go. That area is done. So our last area is going to be our backlight circuit right here, and then this board goes for a bath. So this these backlight drivers can be a pain to solder sometimes. This solder is intact, so I am just going to put a new one on like this because it's still fine. So I'm going to get a little flux around that. We could reuse the original lead-free solder. Let's go ahead and get our resistor on real quick. This is going to be a 0 ohm. That's a 0 ohm. Looks like 402. Perfect. I think it's 402. Might be a 201. No, it's a 402. Either way, you shouldn't use a 201 for something that small anyway, so. Get a new backlight driver. Get a little bit more flux here. I'm going to pull my chip from the donor board. Chip is now fully soldered, so we should be good now. I'm going to do a final pass over, make sure everything looks satisfactory, and it's looking alright. I think we'll be alright after ultrasonic here. This cap right here. Now, we're going to do our same test here. We're going to look at the end caps. This one concerns me here. Because the fact that it's near a coil could also mean it's like a bootstrap capacitor or something. For a MOSFET, and those we can't remove. This is a totally new circuit. This is a 3V8 AON. AON stands for always on. PP bus G3 hot has been retired. It's been replaced by PP bus AON, which honestly makes more sense for always on than G3H. I mean, who came up with G3H? All right, that oxidation is washing away. Yeah, so this one's all right. That's what I look for. I look at the end caps, and this one's fine. A little more flux. This flux I'm using, NC560, is very good at this. It's much better than anything else I've tried for removing oxidation on components like that. So that's why I'm using that and not my usual VS213 or 559. These guys look fine. This one I'll touch up a little bit. And then we're ready for a bath, I think. I'm not going to turn it on with this flux. The problem is that there was a lot of corrosion here, and all that flux is mixed with all that corrosion. So, all right. This is time for an ultrasonic bath, and then we'll be back and look at how this board looks after ultrasonic cleaning. All right, our board just came out of the ultrasonic cleaner and was dried off. So let's go ahead and take a look now and see what it looks like. So this area was all nasty and corroded, and it looks pretty good. This one little resistor here. Little bit of oxidation left, but the bottom solder joint is intact, and that's what I care about. Speaker amp area looks pretty much untouched now. We have a little bit there, but it looks pretty good. It looks pretty good there. All the corrosion is gone, and the remaining solder joints look good. This resistor right here also looks good. Again, I don't really care about the top on resistors. It's the fact that, yeah, see, this is just a layer of oxidation. That resistor is actually fine, so don't let that fool you after ultrasonic, because that can happen. The actual solder joint is fine, and that's what I care about. There's our processor. Now, here's what we really care about. Here's our backlight circuit. Now, you may have remembered this, and it looks pretty good now. I mean, it's not corroded. The resistor looks good. There's no broken solder joints. It looks decent. So this area was all corroded before, and now it is not. It should be good to go. And let's look at the other side. Oh yeah, that's right. I had a little resistor here. Yeah, so this resistor on the battery charge controller, it looks okay. It's still connected, but that one, you may think, well, how do you differentiate between a resistor that you can just leave and one that you need to solder? Well, look at the solder joint. See how the solder joint on that is kind of degraded? It's not fully connected to the board underneath. When the others, the top might have been a little bit oxidized, but the actual solder joint was not. So I'm going to get a little bit of flux here. Don't want to overdo it because it just came through the ultrasonic cleaner. I don't want to make a mess. Just like that. Done deal. Clean that up. We're good to go. Yeah, this looks pretty good. Don't see any other remaining defects after ultrasonic, so it's time to throw this heatsink on and throw it in the enclosure and see if it works. All right, we're back in the enclosure here. Booted into an operating system. You see, still works. I didn't break anything. Just joking there. So let's go ahead and move our backlight brightness slider up, and look at that. It no longer shuts off. Again, I'm holding it at an angle, so I do not reveal any information on the screen. But we can now adjust our backlight brightness, and the display no longer shuts off. So this should be fixed here. One other thing I just want to check really quick is our keyboard brightness, because our keyboard backlight brightness, which still works beautifully because that is controlled by the same chip. So that is all good. So this machine is fixed. This is number 2 of the M1 machine saved. Hopefully we start seeing more of them, because this is definitely an improvement on board design compared to previous models in a lot of circuits. But yeah, this is fixed. Thank you for watching, and I hope this video helps you solve your problem.